As promised, in this segment, we're going to look to see what happens, or begin to see what happens, when you have more constraints than you have unknowns. So let's see what that picture looks like to begin with. All right, let's stick back with our same model of a line, y equals mx plus b. And let's imagine I have not just 2 points for the 2 unknowns, but I have 2, 3, 4, 5 points. All right, so if I gave you these 5 points and I said, please fit a line to them, first of all, can we agree that the points exactly lie on the line? So if I pick these 2 points to estimate the intercept and the slope, or I picked any other 2 lines, any other 2 points, it wouldn't have mattered, right? So in that case, when everything exactly lies on a line, well then pick any 2 you want, I don't care, solve a fully constrained system of linear equations. But what happens when your data looks like this? And by the way, what is this? Well, there's just a little bit of noise in the data. Imagine you're trying to correlate 2 things, how old somebody is to how tall they are. Obviously, there's a correlation there, but it's not perfect. It's not exact. It's not that I can exactly predict your height given an age. So there's a little slop in the data. There's a little noise in the data. There's a little uncertainty in the data. But you can see a clear linear trend. So it's not like you would just say, well, this doesn't really fit a line. It sort of fits a line, but just not perfectly. And of course, these models are just approximations. They're just a way of capturing the trends in the data, whether they be linear or polynomial or exponential or logarithmic or whatever it may be. So what do we do here? Well, can we do the same thing? So what if I just picked these 2 points? Well, now from these 2 points, I would have that intercept and that slope, which looks pretty different than the line I had before. Or I could pick those 2 points, and now I have a negative intercept and a much steeper slope. Or I could pick those 2 points. So picking 2 points doesn't really make sense here, right? Because you can see, and this isn't really a contrived example, any 2 points here give me wildly different lines. And if they give me wildly different lines, well, what am I doing at that point? I'm not model fitting anymore, I'm just playing games. So what do we want to do? Well, intuitively, we want to use all the data. We don't want to cherry pick our data and say, well, these 2 or these 2 are the only ones that matter. All the data should contribute. But how? So let's think about that a little bit. Okay, so well, what are we trying to do? Let's go back to our formulation. We know how to think about this. We want to find an m that multiplies all of these x's, so there's x1 to x5, such that when I add it to b times, of course, a vector of 1s, it should be equal to y1, y2, y3, y4, y5. So that's sort of what we want, yeah? So if I put this in matrix form, what would I have? Well, I'd have a 2 vector with mb over here, and I'd have a 5 by 2 matrix. Well, that's certainly not a square matrix, so that's not invertible. So I don't really know what to do about that. But it's sort of worse than that because there is no m and b that satisfy this equation. How do I know that? Well, because these 2 points lie on a line with that intercept, but these 2 lie on a point with an intercept down here. And so pick any points here, and they don't all satisfy y equals mx plus b. How do I know that? They don't all lie on a line. Now, every 2 lies on a line, but the 5 do not lie on a single line with a single slope and intercept. And so this equation just doesn't get solved. Let's forget about the non-square matrix. This is just not true. Now, everything we've done up until now, it has been true. 3 constraints, 3 unknowns. 2 constraints, 2 unknowns. It is fully satisfied. Okay? But now that we have more constraints that's not perfectly satisfying the model, but sort of satisfying the model, we don't have a mechanism to solve this. Yeah? And we've already agreed you can't just pick 2 data points. That's silliness. Yeah? That doesn't work. So if this was the case, I'd be fine. I can't really quite invert the matrix here because I still don't have a matrix, but I don't have to use all 5 points. I would just, again, pick any 2 points, solve the fully constrained system, and I would be done. And I wouldn't be losing any information. Notice that once I have these 2 points, these 3 points give me no added information. I can throw them away or any other ones. Okay, so we have to deal with this situation. This is the reality. This is the day-to-day reality of data analytics, where you have noise or uncertainty, or the model is just approximately right, and you're trying to fit a trend to the data. So here's what we seek. We seek a line M and B, that's my model, that minimizes some measure of the goodness of fit of the data, x, y, to the model. So what do I mean by that? Well, I think most people are going to agree that this line is a pretty good measure of goodness of fit to the data. It's sort of roughly squeezing between the points. You can think of it as sort of like a slaloming around those, the data points are slaloming around the line. It's certainly better than a line that looks like this, for example, just going through those 2 points, because those data don't satisfy it. And so we want to come up with some measure, obviously we want to quantify this, where we are going to minimize essentially the error or the distance between each of the points in the line, and we're going to minimize some measure of that across all the data. And then the hope is that the line will basically capture the trends in the data and be meaningful to us in a data analytics sense. All right, so here is the measure of goodness of fit that we are going to use. So let me first define a few things. First of all, I have a model that says every point y is equal to mx plus b. Now this is not really quite true. We've already established that because there's noise in the data. So this is approximately mx plus b. Yeah? And let's denote every point as xi, yi, where I is equal to 1, 2, 3, 4, 5, 6 in this case. So the subscript on the coordinates here correspond to the coordinate. Okay, good. Let's measure as the goodness of fit the vertical distance between the point and the line. Now you may be asking why vertical. Hold on to that question. It's a very good question. It is not the only measure of goodness. I could have done the perpendicular distance. I could have done the horizontal distance. But for now, let's just do the vertical distance because you're going to see it leads to something very, very nice. It is this, by the way, as a hint, least squares estimation or regression. So let's pick vertical. And again, I acknowledge, and you should acknowledge, this is not the only measure of goodness of fit. It is a measure of goodness of fit. Okay, so what we are going to try to do is to find the line that minimizes the, let's say, average vertical distance between every point and the line with slope m and intercept b. All right, let's go ahead and define that. All right, so this is where the point is right here. That's xi, yi. And this is sort of where I want it to be, right, on the line. So the first thing we got to do is just figure out how do I define that error. What is that error? Now, obviously, if y in fact does equal mx plus b, well, then the point lies on the line. That's assumed. That then the error is 0. But if it's off of it, well, there's a little bit of error. And what is that error? So okay, so what's the error? Well, it's just the difference between those 2 points. Yeah, so that y and that. Notice, by the way, I don't have to worry about x. So one of the nice things about this measure of error is I have sort of a one-dimensional problem. I just have to worry about the vertical axis. All right, so what is that coordinate right there? Well, it's just the y-coordinate of the point. Yeah, I mean, that is, after all, the point xy, and so that's, let's see, that's the x-coordinate right there, and that's the y-coordinate. So that point is y, right, or y sub I, the ith point. Well, what's that point right there? Well, let's see. It's where the point would be if it lied on the line with slope m and intercept b. Well, where would it lie? Well, what's the x-coordinate of that point? Well, that's still x. That hasn't changed. So if I plug x into this equation, what do I get? Well, I get a point right there, and that seems like the point I care about. So that point is just m x sub I plus b. It's where would the point lie if it lied on the line mb. And that distance, or that difference, or that delta, it probably should be delta sub I, there is an I there, is just the difference between yi and mxi plus b. That's this equation right here. That is just the vertical distance. Now notice, if that point was exactly on the line, then this is still mx plus b, and then the point is at y, but y is equal to mx plus b because it lies on the line, and so the error is 0 because those are exactly the same. Good, that makes sense. Okay, so we are going to try to find a line that minimizes some measure of goodness of fit to the data. We've agreed, and I will agree it's arbitrary for now, that we are going to minimize the vertical distance. We will talk later on about why I made that choice and what other choices mean to the estimation of a model. Okay? That vertical distance is simply where the point is vertically, that's the yi, minus, or doesn't matter what the sign is, you'll see in a minute, where it should be if it satisfied the equation of the line, which is mx plus b here minus where it is there. So that's the delta. Okay. Now notice here that in this case, this delta is less than 0 because this value, this value is larger than this value. Yeah. So I have a smaller value minus a larger value. So that error is negative. Okay. It's less than 0. Now, if the point was below the line, well, then that value is larger than that value, and the delta is greater than 0. Okay. Do we care if the point is above or below? Well, not really. I just want to fit the line, minimizing the distance. I don't care whether it's a negative or positive distance. It's just how far is it. So we got to sort of get rid of that sign, right? I don't care that it's positive or negative. We want to get rid of that. Well, so what are the two standard ways to do it? Take the absolute value or square it. Now I'm going to square it, and that's not arbitrary, and you'll see why. There's a consequence to that, by the way, which I'll explain later on. But for now, let's go ahead and say that we are going to minimize the square of the vertical distance between the point and the line. And let me say again, I've now said it twice, but I'm going to say it 3 times and probably a few more times, is that this is an arbitrary choice of an error to measure for goodness of fit. There are other measures that lead to different types of model fitting, different advantages and disadvantages. This one has some advantages and some disadvantages, and we'll talk about that as we progress downward. But for now, let's just agree that this is a measure of goodness of fit, and I think you'd agree that it's a reasonable measure of goodness of fit. There's nothing sort of bizarre about it. I'm just trying to minimize all those distances. Okay? Good. So how do I minimize all of them now? So that is the error, delta sub I, for 1 point. And now what I'm going to do is just sum up all of those errors for all the points. So let me introduce the summation notation if that's not familiar to you or a little rusty. So what is this? mxi plus b minus yi squared. So that is the error for 1 point. Yeah? And now I'm going to sum, this is a for loop by the way, or a while loop, from I equals 1 to n. So when you see that summation, the big sigma, I starts at 1, ends at n inclusive. That sounds a lot like a for loop, by the way, in Python. So I will take on the values 1, 2, 3, 4, 5, 6, 7, whatever it is. In our case, we only have 6 points. And I'm going to compute this error for I equals 1, I equals 2, I equals 3, 4, 5, and 6. And I'm going to sum them up. Okay? And I'm going to try to minimize that. Now, I could put an average here, so 1 over n. It's going to turn out it doesn't matter whether I multiply by something here, and you'll see later on why that is. So our job is going to be, we now have sort of an objective function, what we call an objective function. We want to find the m and the b that minimizes the average square of the vertical distance between every point and the line with slope m and intercept b. Now I've specified this for a line. This could have been a polynomial. It could have been many other things, but the line is the easy one. Okay? Again, some choices we made here. We chose to compute vertical distance. We chose to square that. And we chose to compute a straight average. All choices. Perfectly reasonable. But there are other choices you can do when you're doing model or data fitting. And they have advantages and disadvantages downstream when you go to try to solve these equations. Okay, so where are we? We started with if you have noise in the data, uncertainty in the data, that the data don't exactly follow the model, what do you do when you have more data than you have unknowns? Well, you can't just really, we saw, pick and choose the data you want. That leads to chaos. It's nonsense. So you got to sort of incorporate all the data. And what we said is we are going to try to estimate the model parameters, equation of a line, by minimizing some measure of goodness of fit. That measure of goodness of fit was the square of the vertical distance between the data points and the line, which we specified as the sum over all data points of the square of the vertical distance between the points and the line. But now we have to solve that equation. So now the question is, how do I compute m and b that in fact minimizes that? So now I have an optimization problem. I have a minimization problem. Find me the parameters m and b that minimize that. Now you could take a brute force approach. You could search over all possible m and b and keep evaluating that error function until you find a minimum. Not very efficient. And what happens when how small do you have to difference between m and b do you have to search over, and how big of a range do you have to search over? And so you could do it, but it's not going to be very efficient. We'd like to do something a little bit smarter than that. And so what we're going to talk about is what is called the closed form or analytic solution for solving for m and b, which is called least squares estimation, by the way, as you've seen in the title and the slides up until now, that will take that measure of goodness of fit, and we will see that there's a very clean and elegant way of solving directly for m and b, which is also, by the way, why we made some of those decisions based on vertical distance and squares, because they lead to a particularly elegant optimization downstream. All right, so when we pick it up, we'll continue on least squares estimation and how we can solve that objective function to find the slope and the intercept that best fits the data. All right, see you in a little bit.